Welcome to BMLabs. Learn clearly, think deeply.
When we try to visualize mathematics beyond our standard spatial perception, we quickly run into a geometric wall. Standard functions map 1D inputs to 1D outputs on a 2D plane, but a complex input, z, requires a full 2D plane. The complex output, w, requires another 2D plane. Graphing both together demands 4 spatial dimensions, tangling into an illegible geometric mass. To track a complex function, we must split the space into 2 side-by-side grids. On the left is the z-plane, the domain containing every input coordinate. On the right is the w-plane, the codomain holding the corresponding output coordinates. A complex function acts as a dynamic rule of transport, dictating the exact movement required to relocate a coordinate from the z-plane into the w-plane. By adopting this 2-plane framework, we can finally begin to visualize 4 dimensions of data through geometric movement. Let's test this system by applying basic algebraic operations, observing how they translate into physical movement. Take the mapping w equals z plus 1. We start by locating an input point, like z equals 2 plus 3i, on the left plane. Adding 1 increases the real component from 2 to 3, leaving the vertical component untouched. In the right plane, the image lands at 3 plus 3i. This addition manifests as a horizontal shift. We can generalize this rule. Adding any real constant to a complex number results in pure linear translation without altering its height. Now consider a different mathematical operation, multiplication by the imaginary unit, I. Let's use the mapping w equals iz and plot a new starting point directly on the real axis at z equals 1. When we multiply 1 by I, the exact algebraic result is simply I. In the output plane, the image appears on the vertical axis. The coordinate has traveled along a precise 90-degree counterclockwise arc. This reveals the underlying mechanic. Multiplying by I swaps the real and imaginary coordinates and changes a sign, transforming basic multiplication into a rotational transformation. These are distinct, measurable actions. Addition slides a point across the grid, while multiplication by I rotates it around the origin. Algebra in complex analysis serves as a literal instruction manual for maneuvering points across 2-dimensional space. The analytical utility of mappings expands when we scale up from single, isolated points to entire continuous boundaries. Instead of one coordinate, we define a continuous grouping of input points, like this unit circle. We label this set T. Our objective is to apply a mapping function to this entire boundary to determine the shape it forms in the output plane. Because a complex function operates on individual coordinates, transforming a set requires a point-by-point construction across the entire domain. We apply our translation mapping, w equals z plus 1, to every single dot along this circle simultaneously. The function sweeps the entire collection of data points across the gap. In the output space, they reassemble perfectly into the image set, written as f of t. Because our applied rule was linear addition, the structural integrity of the circle was preserved during the transit. By observing how a complex function manipulates continuous shapes and boundaries, we map its complete behavior over an area. When we introduce exponents, the transformations begin to distort the plane. Consider the square mapping, f of z equals z squared. When we apply this rule to a rigid square grid, the geometry bends. The coordinates stretch and flare out into a nonlinear web. This severe bending causes a standard 1-to-1 mapping rule to fail. To track exactly how this failure occurs, we isolate 2 opposite input points. Let's plot z1 at 1 and z2 at -1. The arithmetic is simple. 1 squared is 1, and -1 squared is 1. Geometrically, this results in a collision. 2 distinct inputs map precisely to a single target point at w equals 1. To dissect these collisions, mathematicians use a calculation called the inverse image. It works backward, asking where a given output point originated. Let's drop a target point in the output space at w equals 4. To find the inverse image, we run the operation in reverse, asking which z values satisfy z squared equals 4. We find two separate preimages on the left, 2 and -2. There are exceptions to this rule. If our target is 0, both roots collapse into a single preimage exactly at the origin. Computing the inverse image exposes the invisible multiplicities hidden inside nonlinear functions, showing us exactly where the distortion originates. We have cataloged distinct classes of geometric motion. Addition gives us translation, multiplying by I causes rotation, conjugation produces reflection, and squaring generates nonlinear bending. By tracking these physical changes across two grids, complex analysis allows us to interpret equations as a geometry of motion. The entire mapping process operates like a mathematical camera. The z-plane acts as the physical object, and the w-plane captures the developed image. The next step is applying these rules to specific geometries, using the squaring mapping to see how curved hyperbolas in the z-plane are transformed into straight lines in the output space. Understanding this dual-plane architecture is the first step toward visualizing the underlying geometry of analytic functions.
Keep learning with BMLabs. Follow for more simple and powerful lessons.